In this video, we are going to revise the three trigonometric graphs, as well as revise the effect of the parameters in their equations. Now, we start with the graph of y equals sine x. It is a very good idea to try to memorize these basic graphs, okay? So, for example, memorize the values of the x-intercepts and where their peaks and minimum values lie. Okay, but there are some concepts relating to trig graphs that I'd like to revise with you here. The first concept is the period. Now that is the length of degrees it takes to complete a full cycle. Okay, and we see that for a sine graph, the period is 360 degrees. The other concept is amplitude. Now amplitude we see as the measurement between the midline of the graph, which in this case is the x-axis, and the height of the graph. Okay, but when we calculate amplitude, amplitude is actually the maximum value minus the minimum value, which we divide by 2. So it is half of the difference between the maximum and the minimum value. Okay, right. Then I'd like to revise the range, okay, and the domain. Now, the range for a sine graph is from -1, that's your minimum value, to +1. So the range is -1 to +1, whereas the domain is the whole real number system. Going on to the cos graph, again, revise the x-intercepts and the values of the peaks. Okay, if we look at the period of the cos graph, the length it takes to repeat its cycle, and we see that the period is 360 degrees. Okay, the amplitude is still 1. Okay, so we see the amplitude there, the height from the midline to the maximum. And if we calculate the maximum minus minimum divided by 2. So I just want to show you, I didn't do it previously, but the maximum is 1 minus the minimum, which is -1. If we divide that by 2, that's 1 plus 1, which is 2 over 2, which is 1. So our amplitude is 1. Okay. The range for the cos graph is also from -1 to 1, just like the sine graph, and the domain is also the whole real number line. Okay. Moving on to the tan graph. The tan graph is now very different to the cos and the sine graph. And remember that your tan graph has asymptotes, and these occur where the angle is 90 degrees, or if we add multiples of 180 degrees. Okay, where k is an element of integers. Now, asymptotes are where the graph is undefined. Okay, the period for the tan graph is just 180 degrees. And when it comes to the tan graph, we do not talk of an amplitude. It does not have an amplitude. Okay, but we will, where we have a value for the amplitude of the sine and the cos graph, and is represented by A, that A for the tan graph will represent something else, but we'll look at that. Okay, so the range for the tan graph is the real number system. Y is an element of real numbers, whereas the domain, we have to exclude the values of the asymptotes. So we say x is an element of real numbers, but x cannot be 90 degrees or any if we add a multiple of 180 degrees to that 90 degrees. So these x values are excluded from the domain. Looking at the equations of the different functions and understanding the effect of the parameters a, b, p, and q. So let's start with a. Okay, a gives us the value of the amplitude of the graph. Okay, but now the amplitude is always positive. But in our equation, a can be a negative value. So say, for example, a is negative 3. That means the amplitude is positive 3, but what the negative represents is a reflection about the x-axis. So if a is negative, it represents a reflection about the x-axis. Okay, remember, if we reflect about the x-axis, the y-coordinates change sign. Okay, so moving on to b. The b value causes a period change. And the way it does that is that for the sine and cos graph, the period is 360 degrees. But if we divide by that b value, we find the new period. Okay, so if b is 2, we would find the new period by saying 360 degrees divided by 2, which would give us 180 degrees. Okay, now b could obviously also be a negative value. And for the sine and cos graph, that negative represents different things. So for the sine graph, okay, so for sine bx, if b is negative, okay, so in other words, if we have sine of negative x, it means a reflection about the y-axis has occurred. So we have a reflection about the y-axis. Okay, and we see this in the reduction of negative angles. Sine of a negative angle, so here our coefficient of x is -1, which is our b value. Okay, that reduces to negative sine x. So from left hand side to right hand side, the whole expression has gone from being a positive expression to a negative expression, which means that our y values have changed from positive to negative. And changing from positive to negative is a reflection about the x-axis, but if we look at the x values, okay, negative to positive, which is a reflection about the y-axis. So yes, for the sine graph, a reflection about the x-axis looks the same as a reflection about the y-axis. Okay. When it comes to the cos graph, however, so if we're looking at cos bx, if b is negative, no reflection has occurred. And this comes from the reduction, the reduction of negative angles for the cos graph. Cos of a negative angle goes to cos of that positive angle. So our y value remains unchanged. So there is no reflection. Okay. Right, looking at q. Okay. Q, as for every other function that we have studied, represents a vertical shift. And if q is positive, we shift the graph up by q units. And if q is negative, the graph is shifted down by q units. Okay, now P represents a horizontal shift, or we also call that a phase shift. And with all the other graphs that we have, all the other functions that we have studied, if we want to shift right, so shifting right means we subtract from x. Remember, this is counterintuitive, okay? Moving right takes us to the positive x values, but we subtract from x. So if we move right, we subtract, and shifting left, we add to x. Okay, so shifting left, we add a value to x. Now looking at the tan equation, okay, Q is the same. Vertical shift, okay, P is the same horizontal shift, they work the same way, okay. Sorry, I'm just going to change this to having B outside the bracket there. Now, B again is my period change, but I just have to remember that for a tan graph, the period is 180 degrees. So my formula for finding the new period is 180 degrees divided by B. And A, for a tan graph, looking at A, I have to remember that for A, there is, now looking at A, there is no amplitude in a tan graph, okay? So the value A tells us the distance between the midline, or the x-axis, and the graph at x equals 45 degrees, okay? So I'm just going to say that again and write it down. A tells us the distance between the graph and the midline, which is the x-axis if the graph has not been shifted vertically, okay, and the graph, the distance between the graph and the midline at x equals 45 degrees. Okay, so we are talking about this distance. This is our midline, okay? Currently it is the x-axis because our graph has not been shifted vertically, okay? At 45 degrees, the graph is at the y value 1. So the distance between the graph and the midline at the 45 degree angle is 1, which means that our A value is going to be 1. And we will look at another example of a tan graph later on in this video. Okay, now we're just going to look at some graphs and see these effects of these different parameters. Okay, so looking at this first graph, we have the red graph, which is the original sine x graph, and then we have the green graph, which is 2 sine x. So in the equations, compare the A values. Okay, now remember A tells us the amplitude. So for the original graph, the amplitude was 1, and our A value is 1. But for the second graph, which is the green graph, the amplitude is 2, and that is our A value. So amplitude is 2, okay? But I just want to also remind you that we can use the formula maximum minus minimum divided by 2 to find the value of the amplitude. And in this case, our maximum value is 2 minus our minimum value is negative 2. If we divide that by 2, we have 4 divided by 2, which is 2. So our amplitude is 2. So if we look at the graph, we see the amplitude as the peak, the maximum, and the distance between the peak and the midline, which is 2. And if we use the formula, it's maximum minus minimum divided by 2. Okay. I just want to point out that when the value of A changes, if that is the only change from the original graph, the x-intercepts are unchanged. Okay. Looking at another equation where the value of A has been changed, here our A value is 0,4. So looking at the green graph there, we notice that the amplitude is 0,4. So the amplitude is the A value, okay? In this case, again, the only thing that has changed is the A value. So in the second graph, which is the green graph, our A value is -1. Looking at the green graph, our amplitude is still 1. Okay, so the amplitude is the positive value 1. What that negative there represents is a reflection. Okay, so a reflection about the x-axis. And we can see that very clearly if we look at all coordinates on these two graphs. Now what we have is a negative A value greater than 1. So what we see here is a reflection about the x-axis and an extension. So there is a vertical stretching because the A value is greater than 1. So as the A value increases, the graph is stretched vertically. So we see that the amplitude, okay, maximum value minus the minimum value. So my maximum value is 2.5. Minimum value is -2.5. So if we were to calculate it, it would be maximum minus minimum divided by 2, which is 2.5 minus -2.5 divided by 2. That's 5 divided by 2, which is 2.5. So always a positive value. So our amplitude is 2.5, but the negative here represents a reflection about the x-axis. Right, looking at this graph, these two graphs, compare the Q values. Okay, the red graph is our original sine graph. The green graph is the sine graph, sine x, plus 1. So our Q value for the green graph is +1. Now what that has done is it has shifted the graph vertically up by 1 unit. Okay, notice where previously the x-intercepts were unchanged by the change in amplitude or vertical stretch, a vertical shift in the graph does change the x-intercepts. Looking at the Q value here, okay, here we have Q being -2 for our green graph. And what that means is that the graph has shifted down by 2 units. So a vertical shift down by 2 units if Q is -2. Okay, now we have a change in the B value. B is the coefficient of x. So remember that B tells us something about the period of the graph. Now if we look at the original graph, okay, so let me just write in some values here. That's 180, 360. The original graph had a period of 360 degrees. Okay, our new graph, if we just follow it, okay, we see that it takes 180 degrees only for it to complete a full cycle. So our period here is 180 degrees. Now remember that our B value is 2. So if we work with the formula, the period is 360 degrees because we're dealing with a sine graph, divided by B. So 360 degrees divided by 2 gives us a period of 180 degrees for our new graph. Notice that this change in period affects the x-intercepts. Okay, just another B value change. Here our B value is 3. Okay, so looking again at our original graph, this is 180 degrees, 360 degrees. The original period is 360 degrees. If we look at the sine 3x graph, okay, it takes 120 degrees to complete a full cycle. So the period is 120 degrees. If we look at the formula, where B is 3, our period being 360 degrees divided by B, that's 360 degrees divided by 3, which is 120 degrees. Okay, now we have a B value that is less than 1. So here B is 0,5 or a half. The red graph is our original graph that had a period of 360 degrees. Okay, now if we look at the graph sine half x, okay, its period is double that. So its period is 720 degrees. Okay, just looking at the formula. So if our period is 360 degrees divided by b, that would be 360 degrees divided by half, which is 720 degrees. Right, now we look at an example where our b value is negative. And in this case, we have f of x equals sine negative x. The coefficient of x is our b value. So our b value is -1 for the green graph. Okay, now b changes the period, but it is the positive value of b that changes the period. So our period here, we would divide by the positive. We ignore that negative. We divide by 1. So it remains unchanged at 360 degrees. Okay. What the negative tells us here is that a reflection has occurred. Okay. And in this case, we go from a positive x value to a negative x value. And when our x values change sign, we have a reflection about the y-axis. Okay, but we see that this is the same as a reflection about the x-axis. Okay, and this is because of how reduction works. So we know that sine x, so y equals sine x and y equals sine negative x, those two graphs represent a reflection about the y-axis. Okay, because our x value goes from a positive x to a negative x. But we also know that y equals sine negative x is the same as negative sine x, which we know from negative angle reduction. Okay, now here we are going from a positive y value to a negative y value. And when we go from a positive to a negative y value, we have a reflection about the x-axis. Okay, now so that means these graphs are equal. So reflection about the y-axis is the same as reflection about the x-axis in this case. Now we look at horizontal or phase shift. I'm just going to change this to 90 degrees. Okay, so we have our original graph, which is the red graph, y equals sine x, and then we have the graph shifted, and its equation is sine x plus 90 degrees. Okay, now remember that if we are adding a value to x, it represents a shift to the left. Okay, and in this case we are shifting 90 degrees to the left, and we see that. So our value there is 90 degrees, 180 degrees. We see this shift to the left by 90 degrees. Okay, so now we're combining a period change and a horizontal shift, and I'm just going to change the pi over 3 to its degree equivalent, which is 60 degrees. Okay, so what we have here is y equals sine 4x plus 60 degrees. Now there can be some confusion relating to both of these parameters being changed. Now, to really understand the value of the horizontal shift, if you have a b value greater than 1, it is very important that you factorize out that b value from your brackets. Okay, so if I factorize out 4, I'm left with x plus 15 degrees. And if you do that, then there's no confusion about how many degrees you are shifting left or right. Okay, so in this case, our b value is 4, and our p value is positive 15 degrees. Okay, so the b value 4 tells us about the period of the graph. So our period for this graph is 360 degrees divided by b, which is 360 divided by 4, which is 90 degrees. So our graph's period is just 90 degrees. Okay, and the p15 tells us, so from the x plus 15 degrees, we have a shift to the left of 15 degrees. Okay, so from the red graph to the green graph, we shift by 15 degrees left. Okay, notice that that 15 degrees was not what we had originally written in the equation. So if you have a horizontal shift and a period change, it is very important that you factorize out that period change to understand the effect, the horizontal shift that has occurred. Now I'm going to work through 2 graphs, just looking at the equations and making sure that we understand their parameters. Okay, so our first parameter is the a value. A is -2. The negative tells us that a reflection has occurred. And since this is equal to y, the y value has gone from being positive to negative, which is a reflection about the x-axis. Okay, the amplitude, which we also get from the a value, is 2. Remember, amplitude is always positive, so it's not -2. Okay, now the period of this cos graph we find by saying 360 degrees divided by the b value, and our b value is 2. So 360 degrees divided by 2 is 180 degrees. Okay, now to understand the horizontal shift, be very careful. Okay, don't just think, oh, okay, I've got plus 60 in my brackets, it must be a horizontal shift of 60 degrees. Wrong. Why? Because there is a period change. Okay, that period change lessens the amount of our horizontal shift. So what we have to do is, if I have 2x plus 60 degrees in the brackets, I must factorize out the coefficient of x. So I'm left with x plus 30 degrees in brackets, and that 30 degrees tells us our horizontal shift. Now it is positive 30, so we are shifting to the left by 30 degrees. So shift left by 30 degrees. Okay, then we have the q value, which is -3, so that is a vertical shift down by 3 units. Looking at a second function, and in this case a sine function, okay, just understanding what the parameters are telling us. Our a value is 1/2, so that means our amplitude is 1/2. Okay, it's not negative, so no reflection has occurred. Right, looking at the period is changed by the coefficient of x, which in this case is 3. This is a sine graph, so we say 360 degrees divided by the b value, which is 3, and that gives us a period of 120 degrees. Okay, looking at the horizontal or phase shift, okay, it is not 90 degrees. Remember, we have to factorize out the coefficient of x. Okay, so if we do that, we are left with x minus 30 degrees in brackets. Now this negative 30 tells us that we are moving right by 30 degrees. Okay, and the vertical shift is represented by the Q value, which in this case is 4, so the graph is shifted up by 4 units. Moving briefly to the tan graph, okay, we have tan 2x in this case, which is represented by the green. What I have here is the dotted graph, faintly dotted. That is the original tan x graph. Okay, now the coefficient of x here is 2, and remember the coefficient of x is our b value, which changes the period. Okay, so in this case, my new period would be 180 degrees, because we're dealing with a tan graph divided by b, which is 180 degrees divided by 2, which is 90 degrees. Okay, so if we look at the graph here, if we just follow one of its arms, okay, notice that its asymptote is also affected. The asymptote now lies at 45 and negative 45 degrees. Okay, so the period change also changes where the asymptotes lie. So it compresses or stretches the graph horizontally. Okay, now we look at y equals 2 tan x. Now this 2 is our a value. Now where the a represents the amplitude for sine and cosine graphs, a tan graph does not have an amplitude. Okay, so remember that for the tan graph, the a represents the distance between the graph and the midline at 45 degrees. So distance between the graph and the midline, which is the x-axis if the graph has not been shifted vertically, at x equals 45 degrees. Okay, and again, the dotted graph is my original tan x graph, and we see that the original tan x graph at 45 degrees has a distance of 1. Okay, so for that tan x graph, the a value is 1. Okay, now if my x-axis is the midline, for the y equals 2 tan x graph, which is here, okay, at 45 degrees, the graph is at y equals 2. So the distance from the graph to the midline is 2. And that is the a value. So the distance from the graph to the midline at 45 degrees is your a value. Now, looking at a tan graph that has an a value and a vertical shift. Okay, so first understand that, let's change the color. The vertical shift here, represented by the Q value 1, is a vertical shift up by 1 unit. Okay, which means every point has been shifted up by 1 unit. Okay, so that also means that the midline has shifted up. So your x-axis is no longer your midline. The line y equals 1 is your midline. Okay, so if I want to calculate the a value or show the a value, okay, I look at the 45-degree angle and the distance of the graph to the midline at 45 degrees. 3 minus 1 is 2, and that is our a value.